Welcome, everyone. And tonight we have Charles Osborne here to speak with us on radio astronomy for amateur radio, K4CSO. I heard about this presentation through several club members who just ranted and raved about how good it was, and when I heard about it I said, wow, radio and astronomy. I remember growing up, 10 or 11 years old, I always had my little walkie-talkie radios and a telescope. And now, a few years later, I have a bigger telescope and more radios than my wife knows about. So. And she knows that too. She won't look. But Charles was kind enough to send his resume over to help me out with the introduction. And to be honest, I didn't understand half of the stuff that was on there because it's some heavy-duty stuff that Charles is into. He's an extra class license holder, Bachelor of Science in Electrical Engineering from North Carolina State University. And he's worked at a variety of high-tech firms. The ones that stood out to me were AT&T, Rockwell Collins, Scientific Atlanta, even Georgia Tech Research Institute, among others, in a wide range of microwave systems engineering and related roles in that field, and we'll probably hear him mention some of that today. He was elected president of the Society of Amateur Radio Astronomers from 2002 to 2008. He's founder, chief technical officer, and director of the Southeastern VHF Society, president of Southeastern VHF Society from 2010 to 2013. He holds was awarded the Southeastern VHF Society K4 UHF Award, which is for lifetime achievement in experimental engineering and educational contributions to the VHF, UHF microwave aspects of the amateur radio hobby. And I thought this one was really cool. This is just about 3% of what he's done, but this stuff I thought was pretty cool. He was the Hughes Award winner, which was Teacher of the Year for Gwinnett County Schools in volunteer science teaching. And a long list of articles that he's written, periodicals that too numerous to name here. But great work, Charles. And he's our microwave Jedi. We had a Jedi here last week on FT8, and my goal here is, before I finish out the year, is to have a Jedi come to every meeting. So we'll see if we can score as high as Charles for next month. But we're ready to get on with it, Charles. If you want to take it away. Thank you.
Okay, let's see how this works. All right, well, glad you invited me, and I'll try to do my best to live up to that build-up. Yeah, I just told him, pick whatever you want out of the resume. Yeah. Okay, yeah, go ahead and bring up the first one.
Yeah, give me 1 second. There we go.
Okay. Okay. Now, I'm going to go through a wide variety of areas that are of interest to hams. I think you'll find out you've been doing radio astronomy all along. You just didn't know it, perhaps. So there's a bunch of different areas that every time you turn on an HF rig, you're doing radio astronomy. I mean, think about it. Everything about HF is related to the sun. So solar activity is very important. That in itself, every time you listen to the noise, you're listening for that weak signal. A lot of that noise comes from the galactic background noise. So there's all kinds of radio astronomy going on. It's just a matter of knowing that it's happening. Okay. Okay, this is a good group. And I know they're going to try to post this on the website, the whole presentation. So there's a lot of links in here that if you decide later you want to go back and dig in a little deeper. The Society of Amateur Radio Astronomers is a pretty good group. It's about 300 members in 17 countries. So they cover a wide variety of radio astronomy topics. We're set up with a lot of different subgroups that specialize in very low frequency or solar astronomy or pulsars. And so we'll go through a sampling of a lot of that, but there's a lot more. So if you go to this website, radio-astronomy.org, you can dig in a little deeper and maybe get some direction out into other areas. And we also have a chat, kind of a reflector, list server, so there's a lot of online help from other members that you can connect up with one-on-one. Okay, and I'm going to skip through a good bit of this. It just depends on the interest level. So if you have a question, I'm going to try to move right along so that I don't get caught up in the math or anything that if I see people dozing off, I'll go faster. So the sky isn't always clear. But for one thing, there's a lot of people that got into astronomy because of Astronomy Magazine or all the pretty pictures that you see for optical astronomy. And but very quickly you find out that you're not going to do that with your telescope. You buy a bigger telescope, you still don't see all the pretty colors and things. So it's a very kind of a disappointing thing to some people that you just can't get those exciting pictures without spending tens of thousands of dollars. Now, there are some tricks to that today, and it also involves more than just optical astronomy. Radio astronomy is also becoming a remote observing area also. So just like you can get online and find a receiver somewhere in the world on the internet and listen to it, you can do the same thing with optical astronomy. There's telescopes out there that you can actually buy time on. And also radio astronomy. So there's a number of interesting areas like that that the internet has allowed us to do. Okay, the key things though is there's a lot of background in astronomy that's good to know. And actually our cell phones have become an interesting tool for this. There's a lot of apps that if you see a star over here and you're curious, what is that? Bring up an app on your cell phone, hold it up, and it'll tell you what that is. Is that Mars? Is that Venus? Is that Sirius? So you can do a lot of learning by trying to figure out, well, what am I looking at in the sky and where is it? And there's a whole different coordinate system for astronomy, right ascension and declination. So if you're looking at some of the magazines, you can actually go in there and you'll see a grid overlaid. It's kind of like latitude and longitude, only projected out onto the sky. And it's fixed in a way that if I tell somebody go to right ascension 18 declination 23, you can then go to that on a map and see what's there. So it's like the latitude longitude thing, only for astronomy. So that's a good basic thing to kind of get an idea of what you're doing, and of course get an idea of where the North Star is. There's a lot of tricks to figure out if you're looking at the right thing in the sky. So generally, figuring out where the North Star is a good place to start. There's a lot of interesting things as far as figuring out how the sky moves. If you actually look at the way the Earth goes around the sun, if you're pointing at the same celestial target, it's going to be coming up about 4 minutes quicker each day. So you end up with they call it the sidereal time, is 23 hours and 56 minutes instead of 24 hours because of the way we're going around the sun. So if you take 365 days and divide it out, you end up with that 4 minutes in terms of looking at the sky. So that's why things gradually change over a period of time, and that'll come up again in a couple of slides. So flip through this, but this is kind of one of the key things to figure out that you've got a celestial equator, 0 degrees, figure out declination relative to that. And it, again, the cell phones will help because you can bring that map up on top of the objects that you're looking at. And this is kind of a simplified astronomy chart. I like this particular program because it doesn't overcomplicate things. A lot of the programs try to be all things to all people. So they'll put so much stuff on the screen that you're just lost. You look at it and you say, I can't even find a single constellation there. There's just too many stars. So a lot of the programs you can adjust so that you only see a few constellations, the bright stars, the key ones. And that helps you figure out what you're looking at and learn it. But anyway, this kind of program, actually, this one's so old it fits on a floppy. So I use it a lot with teachers, or I did in the past, because it would run on almost anything. But of course, as soon as we got into Windows 7 and Windows 10, then it quit working. So something about it wasn't compatible with anything past XP. But it was a good program. It's only about a megabyte, and it actually gives you the elevation and azimuth of the targets. So you could at a particular time go up here and click on Orion, and it would tell you what the azimuth and elevation was where you could point at that. And of course, as I mentioned, astronomy is a daytime or nighttime if you're doing radio astronomy. So that's a big advantage. Do it whenever you want to. So, but you got to know what you're looking for if you're doing it in the day, because the constellations are still up there. You just can't see them because the sky's bright. So for radio astronomy, that learning the mapping is pretty important. Okay, everything has a temperature, at least I hope so. So everything generates RF. There is some measurable amount of RF radiation coming off everything, including people. So as you measure the temperature, well, you can actually do radio astronomy, and they talk in terms of temperature quite a bit. In fact, it's fairly confusing because everything is Kelvin this and Kelvin that. It's physical temperatures, it's brightness. So there's a lot of things that go into the figuring out the strength of signals, and it's relative to how hot they are. So they take they actually calculate it back to the temperature, let's say, of a 50 ohm resistor, and how much equivalent RF comes out of it. So that becomes, how hot would I have to heat this resistor up to get that much RF out? And so that some of this is called KTBS. It's basically Boltzmann's constant and some math related to the bandwidth and temperature. Okay, and there's a variety of different ways that we look at astronomy. A lot of what goes on is actually based on emission or absorption. So when you look at an object out in space, let's say it's hydrogen gas or the sun or whatever, there will be spectral lines that are generated in the optical range that tell us what that's made of. And you get a lot of frequencies that actually help in radio astronomy tell what that particular astronomical area is consisting of. So in this case, we're showing the spectral lines for sodium, hydrogen, calcium, magnesium, neon. And so in the radio realm then, let's see, there we go. In the radio equivalent, you would have like hydrogen putting out 1420.405 megahertz. Or deuterium puts out 327.384 megahertz. You go down into some of the methanol, 6.668 gigahertz. So a lot of astronomy is trying to find these molecules by their radio emission frequency. So that's why you got a big dish. These things are pretty weak. So they don't put out much signal, and to actually pull that signal out, you're also dealing with Doppler, because a lot of this stuff is moving very fast, and so it gets smeared out by the speed that it's moving. So in some cases it's hard to tell what you're looking at because it's shifted to a new frequency. But eventually there's enough clues that you can figure out the speed and then correct for the speed that area of space is going, and it gives you an idea of what's going on there. So anyway, that's a lot of the frequencies that come out. Hydrogen line is one of the most pervasive. This 1420.405 frequency is from the most common atoms out there, which is hydrogen. And the electrons spin flip. In other words, when it gets energy, it's rotating with the poles opposite. And then when it gives up that energy, it flips the other way. So low state and high state of energy. And that little bit of energy that gets sent out when it does that flip is 1420.405 megahertz. So, and that's one of the easier ones to receive. Actually, you could pick that up with software-defined radio, low noise amp, and a dish about that big. So we've actually picked it up on like a 3-foot dish with a good LNA and a software-defined radio.
Where does that dish need to be in terms of isolated from background noise? How much harmonics from the radio
Everything.
stations and television stations?
That is a problem. Yeah, you can, I mean, if you pointed at something that's putting out, let's say the radar over at Dobbins is a prime example. That's at 1295 and 1290 megahertz, really strong. You can hear that without an antenna on 1296. So if your software-defined radio gets that strong signal from a radar sweeping through, yeah, it'll show up. So its desensing effects are pretty challenging sometimes. But like everything else, you put a good enough filter in front of it, you can get rid of some of the problems from GPS or airport radars. But 1420 is one of the easier ones to deal with. And if you point at the Milky Way, basically, you're looking for that bright band in the sky. If you go down, usually within about 20 degrees of the horizon is the brightest spot. So you're looking at galactic center and around that by maybe 10 degrees. And it's pretty strong. So, and you also can see beyond the galactic center. So if you think about that, you're actually DXing 26,000 light years. You're picking up that signal. And if you can see the other side, which is going at a different Doppler shift, you can actually separate the two. You can see the stuff coming towards you and going away from you, and see those two on the screen at the same time. So then you're looking beyond the center of the galaxy. So another 30 to 40,000 light years roughly.
Is that considered a microwave frequency?
Yeah.
Or UHF?
Well, it's L-band, it's 1.4 gigahertz, so,
Can it be downmixed where you can hear any of it?
oh yeah.
Okay.
Yeah, I mean, yeah, it's, doesn't sound any different than if you were listening to HF noise. I mean, you really don't hear tones because it's noise. Everything's kind of smeared into a blob of stuff that's moving at varying speeds, but you'll see a peak that's kind of in that 1420.405 range. Okay, well anyway, there's a lot of other sources of signals out there. And the microwave range is full of, well, radio astronomy goes on up to beyond a terahertz. So they're actually looking for molecules that are up in the 1,000 gigahertz, terahertz range. So it's a pretty big area up there. There's nice, relatively clear spots as far as looking through the atmosphere. So that helps, and through the ionosphere. And there's a lot of very energetic things out there. Some of these, like this one, for instance, is a pulsar. So you've got what's called a bipolar outflow, and the pulsar generates a fairly strong beam of energy. And so I'll play an audio of one of those in a little while that shows the pulsar sound. And you would think at first that is some kind of pulse that's coming off, but no, it's just continuously putting out a signal, and we just happen to be in the beam as it sweeps through. So it's kind of like a lighthouse, and we just happen to see that flash every fraction of a second. So some of these things are spinning incredibly fast to be a star and to be rotating at 1,000 times a second. That's pretty amazing. Okay, this one you might find interesting, a 20.5 megahertz collinear array. In 1933, Carl Jansky actually built this in order to diagnose where they were picking up noise on international communications. So he built this thing. It's got Model T wheels, so it runs around on a little track, and it's wood mostly through here, and then these areas are copper water pipe going up and down through there. So there's actually a working version of this up at the National Radio Astronomy Observatory up in Green Bank, West Virginia. And they actually still bring the coax into one of the meeting rooms, and you could hook up your own receiver to this thing and listen at 20.5 megahertz. Now, of course, modern technology has made it a little more tricky. There's plenty of digital noise challenges in that range, but they found, in other words, their lab was a really strong source, even though they had worked hard to try to quieten it down. But the interesting one about this particular one was that initially he thought it was the sun. So he was rotating this thing around. He was looking at where the beam coincided with the noise, and he kept measuring it, and over a period of months it started moving away from the sun. And so then he started figuring out, oh, this is associated with something else in the sky other than the sun. And so he was one of the first ones that figured out that it was actually the center of the galaxy that he was here. So that made the newspapers and everything. And eventually they named the unit of signal strength after him. So in radio astronomy, the measure of how strong a radio astronomy signal is measured in Jansky. Yeah, it's a really small number. Okay, shortly after that, and this is around 1932, a fellow named Grote Reber came on the scene. He was, let's see, about 20, I think, and decided he was going to build a dish. Now, at the time, nobody was building dishes, so this was very forward thinking of him, that he wanted to do radio astronomy, but he didn't want to do it with antennas that were the conventional type. He was looking at it more in terms of an optical astronomy telescope and thinking, I should focus all that energy on a receiver. And so he built a receiver, he built the dish. The dish was made out of sheet steel that would have been formed into a fender for a car, let's say. So it's just a thin piece of metal that he could get in relatively large sizes. And most of the dish is wood. So it's quite a construction project for a 20-year-old in his backyard in Ohio. But he was successful in mapping some of the sky with this. I think it was in the 600 megahertz range and also around 2 meters that he built receivers to do some mapping of the sky.
How big is that dish?
I forget, it's like probably 30 feet or 28, somewhere right in that range. Good size, and it's also at the National Radio Astronomy Observatory. They've got it sitting there.
Break it out.
And a lot of his equipment's in the museum there too. So he was an amateur, W9GFZ, and eventually became the National Radio Astronomy Amateur Radio Club call sign. So here's their card. So that's the 100-meter dish at Green Bank, West Virginia. It's about 500 feet, I think, from here down to the ground. It's the biggest dish that's fully steerable, so it can point anywhere in the sky. And it's an interesting place to visit. It's the National Radio Quiet Zone. Has anybody heard of that one or seen the TV spots on that? It's as soon as you come into West Virginia from Virginia, you start losing cell phone coverage. And when you're here, you're about an hour's drive from the nearest cell phone coverage. So just turn it off. There's not much chance of having any cell phone coverage there. The employees at the facility sign a thing that says they won't have a microwave oven in their house because they're doing radio astronomy at 2.45 gigahertz, and that's where the microwave ovens are. There are 2 on site, but they're inside shielded enclosures. So it's an interesting area. I mean, it's very picturesque, farmland and all that. So nice place to visit.
Do they always build radio telescopes buried in the valley around mountains?
They do try.
In unpopulated areas?
If you're into radio astronomy, you like to live in remote places. In the professional realm, they are tops of mountains and very remote sites, because you can pick up a TV station with something like that from 1,000 miles away. I mean, You're going to see reflections off airplanes.
And the TV station signal is much larger than what you're looking for.
Yeah, typically the signals are under minus 200 dBm, if that means anything to some of you. It's just minuscule signals. And so they have to integrate it for a long period of time. It's like taking a time exposure with a camera. I've seen stuff that they've done where they had actually integrated for what amounted to months of time. So they can actually append days on top of it. In other words, they'll track an object for 10 or 12 hours and then stop and then somehow continue the next night and add more on something that's really weak.
I got the chance to buy a nice truck last December. It's a Honda Ridgeline. Looked in the manual, just happened to wanted to read through something, and I was looking at it yesterday. The very first page is a list of all the RF emitters in that truck. That blame truck has about 9 different transmitters in it.
Yeah.
Everything from the window system to the locks to connecting whether or not there's Bluetooth. It's got a connection to the internet. It talks to the Apple Talk. It's got a thing linked back to Honda Link. Can you even drive? Would I be banned from the entire state of West Virginia? How do they enforce this?
I should have put a picture of it here. As you go into a section of the observatory, there's a sign, like you're coming up to a railroad crossing, with a big circle with a red arrow, through it. Says no spark plugs beyond here.
Oh.
So it's all diesel. So diesel is okay beyond that gate, but of course you still got the computers in the cars.
So for 30 or 40 miles around that dish, there's no...
No, it's just on site in the actual observing area. They can't control it once you get out in the public spot. They just try to work around it as best they can. I mean, you can imagine people drive in with cell phones and everything, still searching desperately for that next cell tower. So they're pinging away.
That's the highest power they got.
What is the farthest distance they've been able to measure?
You mean receive a signal?
Yes, that they can measure distance to an object. What's the farthest that they've been able to do?
That's the edge of the universe.
Yeah, I mean,
14.7
billion light years. Yeah. So I mean, it's some of the furthest things out there they can't really see optically, but they can see radio signals. Yeah, but there's some really big explosions and things out there causing that to get that kind of distance.
To answer the question as far as distance, you've got the cosmic background microwave radiation. That's pervasive across the entire universe. So you're talking billions and billions of light years.
Yeah, I mean, I don't know what range limit is. It's like asking a ham, how far can you hear?
So I guess if you think through it, it would be 14 billion light years, roughly.
Yeah.
Yeah.
I love science programs. Regarding matter and antimatter in the explosions that creating 100% energy.
Yeah.
Is that something that you're speaking of? Billions of
Yeah,
years away where those explosions have taken place?
It's probably more like black holes eating black holes and things colliding with two neutron stars hitting each other head on. There's lots of energetic things out there. And the matter-antimatter stuff will generate a lot of temperature, so that in turn will generate a lot of broad spectrum radiation too. Gamma rays. Yeah, the gamma rays are something we don't want to have because that's pretty deadly to people for a long distance. So there's some gamma ray bursts out there that we're kind of worried that we don't want that within, say, 10,000 light years or some relatively large number. Uh-huh.
What's primary study in this?
How do I say this? They have been cut in funding a few years ago so badly that actually a large portion of their funding now is Russian satellite downlink. It's the one that's paying for getting downlink off one of the satellites because they're in the right place, and also SETI. So a lot of stuff was pretty much banned from using public funds to do SETI, but a lot of this has gone private now. So SETI came in, loaded them up with computers, and so a lot of the stuff that the dish would be looking at, they may be doing astronomy in the front end, pointing at something, but they'll be doing SETI search on that IF constantly. You ever read?
A rhetorical question. What is SETI?
Yeah, search for extraterrestrial intelligence. Yeah, I'm not a big proponent of that. You might think I'm in radio astronomy, that's the natural thing, but no, I'm pretty sure we're on galactic quarantine. They're afraid we might be catching. Okay.
Who owns and operates that telescope?
It was the NSF and a consortium of universities. Now it's still got some NSF money, but they're basically having to go out and find their own funding. So they've lost a lot of employees and usual downsizing and stuff like that. It takes a lot of money to maintain something. A 100-meter dish, it's basically like a ship. You start painting it and you never stop. By the time you get back to where you started, that's ready to be painted again. So there's a lot of maintenance on something like this to keep it from rusting or getting damaged by ice and wind and stuff. Okay, that's one of Groth's pictures that he did back in the 30s, just point by point, writing down signal strengths and plotting it out and figuring out what the galaxy Milky Way looked like at 2 meters. And well, this one says 480 and 160 megahertz is the two frequencies that are up there. Okay, this one's Jocelyn Bell, Burnell. She was a grad student who discovered the first pulsar. Didn't get much credit for it because her professor took and wrote it up, and of course he got the Nobel Prize or whatever, but she said, she's an interesting person. She said, it would have cheapened the Nobel Prize to be giving it to graduate students, sort of, words to that effect. So she didn't really think she did anything other than just the drudgery of copying the data down and maintaining the observations and stuff. So she let her professor get most of the credit, but we know her name. So,
Who is the professor?
Anthony Hewish, I think.
Who cares? She discovered it.
Yeah. I'll put her name up there.
Matter.
Give her all the credit I can.
She just, yeah, but he got the prize.
Bigger than.
Okay.
Yeah, but she was just recognized a couple of weeks ago.
Yeah.
They awarded her something like $3.6 million, and she turned it down and redesignated all to fund research. So
Good.
she's been recognized.
Okay. All right. Well, anyway, you can kind of see in the background, this is an HF antenna. It was a huge collinear array, 2,000 dipoles. So there's a lot of stuff to maintain to keep that working. Let's see. You want to play the pulsar sound? This is not necessarily the pulsar that she heard, but that's what one would typically sound like. So that's a star that's spinning at that rate.
Named it after a watch.
It's dance.
You gotta be
Okay.
kinda old to get that one.
You like that?
That's one of the, well, it's one of the more obvious things that you can listen to. Now that's a hard one. It's weak, it takes a lot of antenna, a lot of processing, and a lot of the people that actually do this do what they call time folding. They actually receive the same signal over and over and digitally overlay it. And so that allows them to actually see something that's much weaker. But because they're folding it that way, it's not as easy to actually listen to it. But they can get a good picture of what they're seeing in terms of signal strengths. Okay, and we've gone through this. This was in the lead-in picture, but this is kind of what the sky looks like if you were doing the Mercator projection or whatever, where you see the Milky Way. Center of the Milky Way would be like here, and this is what you're seeing in the sky. And there's a few bright spots that are other things, like there's the sun in this particular picture. I think that's the moon. There's probably a couple of planets. Yeah, Neptune, Uranus, Jupiter. Jupiter is a big emitter. We'll get to that. And of course, if you look at other frequencies or wavelengths, the things can look entirely different. So it's kind of, radio astronomy can see through a lot of dark matter and things that are out there that some of the other wavelengths get absorbed by. This is kind of a neat poster NASA did where they took radio, took pictures at hydrogen, 2.5 gigahertz, infrared, different frequency of infrared, optical. So here's the optical equivalent spot in the sky, and then this is the same area at X-ray and gamma rays, and then all these other frequencies. So it looks very different depending on what frequency you're looking at. So there's a lot of different things going on up there. Okay, those are just some pretty pictures, different frequencies. Of course, and there's Arecibo, that's 1,000-foot dish. Here's the feed. This actually is there's an 85-foot dish inside that pointed down, and then about a 15-foot dish pointing up. So it's a folded optics feed inside there. That dome is, let's see, I think it's 180,000 pounds just for the round dome and the feeds. So when they lifted it from down in here on a kind of a stage, and that was a 180,000 pound lift. And everything else that's up here hanging from these cables is about 1 million pounds. So that's quite an accomplishment to keep that working when they've got the...
They moved that and pointed to different places.
Yeah, the part that moves, this feed right here, goes on this track. There's a track that goes on this kind of a curved section. And then the whole thing spins around an axis that's right here in the center of that triangle. And so doing that, they can only point at stuff that's about plus or minus 15 degrees from dead center up, so zenith. So they're fairly limited in what they can see, but if it passes through that 30-degree circle, then they can track it for a little while.
Is that the one in Puerto Rico?
Yeah.
How did it survive?
It is amazing that it did. Yeah, that's what I'm saying. There was damage. It's hard to see in this picture. In fact, I haven't seen any pictures that actually show the part that fell, but I think it's right, yeah, right here. Right here, there's a waveguide feed that is 75 feet long and weighs 10,000 pounds. So when they do moon bounce, they're using that feed. That's 432 megahertz line feed. And there's waveguide at 432 megahertz, which is the size of air conditioning duct, that goes all up through here, and it's on this catwalk roof all the way down through here, and it goes over the side of the hill down to where the actual klystron is. So this is the source of the most powerful transmitter on Earth. So that's the strongest signal that we can put out, is the gain of this dish plus that 1,000,000-watt CW transmitter. It's like 50-something dB gain antenna and 1,000,000 watts key down.
That's where are they focusing?
They can actually do radar pictures of any of the close planets that are within the beam. So it's kind of an interesting radar. Most radars, you send a pulse and then you listen. And you listen to the pulse come back. Well, if you're sending it to Mercury, let's say, you key down and you stay keyed down for 30 minutes until the signal hits Mercury and comes almost back to you. Then you switch over to receive. So you're receiving a half-hour pulse coming back. So anyway, it's kind of a neat, there's a lot of interesting stuff. I got a whole presentation on that particular antenna. But yeah, so that's a neat thing to see, but it's certainly not an amateur thing, other than Joe Taylor using it with WSJT mode to do EME. And it was loud. I mean, I was listening when they were doing the EME, and you could hear it 15 minutes before the moon even got in their beam. They were already audible. And then by the time it was actually in the beam, this is just with 4 Yankees here in Duluth when I was listening to it, it was like 10 dB to 20 dB out of the noise. So very easy copy.
Yeah, back in the olden days, in the late 60s, there was a big moon bounce activity on 432 from Arecibo. A lot of the guys up in Columbus, Ohio, Big Ear territory, got on the air and worked at CW, just plain CW.
It was probably the same feed and same waveguide. So that 10,000 pound 432 feed did break off during Maria, the hurricane last year, and dropped through the dish. So the dish is, let's see, it's 500 feet from here down to the dish. So it probably made a pretty big hole. So I don't know if they got all that fixed or not. And they too are on, their funding was cut pretty bad 2 or 3 years ago also. So I assume that'll hurt their 432 activity, and the planetary radar won't be up and running until they can get that feed fixed and put back up or replaced. Okay. Everybody knows about the VLA. That's another good one. That one's 72 megahertz to 24 gigahertz on each dish. And of course they can move the dishes around. They've now updated it to where it's on fiber optics. So originally it had waveguide to every dish. So it was a challenge. I think they ended up blowing fiber through the old waveguide to actually get the cables back to the center facility.
Those all have to be phased in phase.
Well, see, they can do that digitally though after the fact. So it's not as hard as it might sound. You take each dish individually, record the signal, and then you run it through an autocorrelator, which puts the right delays in everything. So that's a little trick that they do in the cleanup software afterwards. But you're right, each dish has to be pointed at the same thing, and then they combine all the signals to get the sensitivity.
That's what they use to talk to the Voyager satellite?
Yeah. Well, that's another good one. Everybody knows, they see these things on a lot of commercials. There is no transmit capability in a lot of these facilities. So they just, anything that looks nice gets used in the ads. But they're not radars, they don't transmit. Arecibo is one of the few that can actually transmit. Everything else is receive only, and they're in a quiet zone, and they really don't, they want to be there because it's a remote facility. Okay, let's keep on going. Okay, now we're into ham dishes. Yeah, this is Ray. Ray in up near Gainesville. Ray built all these dishes, and so he's on EME on everything from 6 meters through 2304, I think.
Yeah. But it's all in the workers.
Yeah, it's quite a construction there.
So what multiple of the wavelengths?
Your dish, well, got to make sure the holes in the dish are 1/10 of a wavelength or less. So the screen's got a kind of your limiting factor. The dish size, until let's say at 432, a 10-foot dish or something is about as small as you can go, because you can do just as well with 4 Yankees. You don't get that much gain. It's basically the capture area of whatever you're looking at. So a 36-foot dish would have a similar capture gain of, say, a Yankee array that took up the same amount of space. One of the advantages, though, is that it blocks noise from the ground behind you. So it's a better reflector and a more easily controlled antenna. Trying to phase up all the Yankees is more difficult than trying to do one good feed and put it in the right spot, and then design it so that it illuminates the dish just right. Yeah, back.
So does it have a reflected image?
Does it have a reflected image?
Yeah. Is there an imaged antenna for this, to a dish?
What do you mean?
Is there an antenna that's the opposite polarity of this thing?
Opposite?
There's no
I'm
image
not
in the
following you.
ground.
Yeah. There's no image in the ground.
I mean, like a ground plane?
Oh,
Yeah, on the other side of the ground.
no, I don't think so. I mean, it's ray optics for the most part.
Okay.
So it's, it's got optical equivalence.
Yeah, talk about a backlobe from the edge, scattering
So
from the edge.
it's a
but-
parabola, right?
Yes.
Yeah, I mean, you do try to keep from seeing the ground, so you want the feed to illuminate the dish and not get beyond the edge, or you'll get into you'll create more side lobes and stuff.
Okay.
Like Kathy was saying, anytime you get near the edge, you're going to mess up the pattern.
Could you back up a couple slides there? I saw an old friend up there. Okay.
Not that one.
Keep going.
This one's my dish.
Go back, the other direction. Yeah.
That one?
Right there. I was up there this year.
Okay.
And they still got a little bit of research stuff going, but it's mostly for schools
Yeah.
and volunteers and stuff. We don't have much fun to do.
Yeah, I was one of the first employees there.
Actually, was up in one of those
1999.
back in 66, when it first got installed. I was up in one of those dishes. We were doing some further satellite stuff.
Probably this one.
Yeah.
Yeah, those were both done in the early 60s for NASA. Weather satellite downlinks and some of the other telemetry and things from the Apollo and Gemini, I guess.
Gee, Wes, can you tell us about it without having to shoot us?
That was Applications Technology Satellite Program. They got kicked off there. They've actually got one of the satellites there on display in the museum.
Oh, okay, yeah. Yeah, they've got a full-size satellite in the facility there. Yeah, I was telling them they should power some of it up. They wouldn't let them do any mods.
Does the scientific community, astronomy type specialty, do they feel this is interference?
What do you mean interfering?
Well, anything that we do, RF and
Oh, yeah. I mean, hams are a minor thing because generally hams are pretty accommodating. So you're not gonna, if you know you're interfering with them, you're probably not gonna be on the air. And they're usually good to work with. I mean, they'll tell you if they're seeing you and they've got your phone number, they'll ask you, they might call you up and say, "Are you on the air right now?" Yeah, we're seeing that. Could you go off? Kind of thing. But for the most part, they just work around it. It's such a complex environment to keep clean. Everything from garage door openers to, electric blankets, just all kinds of stuff make interference. They have a full-time employee at a lot of these places that has to go out and track down interference, particularly NRAO. I mean, I was the one for this facility that was trying to keep the cell phones in the right spots. And so they had to go through me as far as approval of where the cell tower was, because the county didn't want to jeopardize the facility. But it was pretty easy to do. You just keep cell phone towers at a certain spot, or you put them behind a hill so that they throw a shadow towards the facility. It's when they want to get up on the Blue Ridge Parkway and cover wide areas, and it gets down in there that makes it difficult. Okay, move along here. Let's see, these are kind of neat. As far as a neat trick, the DirecTV little dishes, you can actually detect a human with those. The thing on the table here is like a field strength meter. It's what they use to point the dish initially. So it's a little meter that reads out, and it usually has an audio tone that shows when you peak it. So you can kind of keep tweaking on that until you get really sensitive. And I think the next slide shows me working with students. And so in this picture, we were trying to peak it on the sun. So if you actually had one of these dishes, the shadow of this feed, when it hits right here at the root of the feed arm, that means you're pointing at the sun. That gets you close. And then the little meter can give you a tone that helps you peak it up even more. But the students were really impressed because you could turn that dish down then and point it at one of them and go back and forth and find them, because they're putting out RF, not from cell phones and whatever, just the fact that they're thermally hotter than the background. So you can see quite a bit just with a little dish like this to show off the fact that you can see the moon or the sun. Moon's a little tricky because it's not that big a signal, but it's kind of a simple thing. We call it, it's one of the key projects in the Society of Amateur Radio Astronomy. We have a lot of these out in schools and groups that do science projects, and we call it the itty bitty telescope.
What frequency?
It'd be about 12 gigahertz. So it's just a standard LNA that's already on there. So they throw these things away all the time, you know, and upgrade them to some that have 3 and 4 feeds, but the dish is still basically an 18-inch dish. It's just putting more than one beam out from the multiple feeds.
So is the LNA right at the focal point?
Yeah. Yeah, it's right here's the LNA, and there's the feed and the waveguide going back into the LNA. Okay, VLF is another, this one is probably one of the spookiest ones that I enjoyed working with. Low frequency, you know, 50 kilohertz and down. These are really low frequency. You'll find beacons going out to submarines, lots of different slow speed data kind of links to things like that. But the actual Earth astronomy part of it involves the inbound cosmic rays and things spiraling in on the magnetic field lines of the Earth, and so you get a lot of interesting sounds. Let's see if we can play this one. Sounds like a science fiction show, but this is actually what you hear.
What is it?
Yeah, it gets more interesting near the end. It almost sounds like a pond with frogs and stuff making noises. These would have been around 50 kilohertz. But some of this is on down in the audio. All these little things have different names. Whistlers, spherics, dawn chorus. The dawn chorus is the one that sounds the most like a pond with frogs and stuff going. But to think that that's, you know, natural noises. In fact, that's the, if you wanted to hear more of these, that's kind of what you search for online, natural radio. We'll get into some of this. Natural radio and VLF is good search words for this kind of stuff. And so the Society of Amateur Radio Astronomy builds up these little receivers and then sends them out to, let's say, high school science students. And then they'll do listening projects with this. So there's, I forget how many thousand they've done, but it's quite a few. And the antenna is just loops of wire around a PVC frame. There's a bunch of different VLF loop antennas designs out there.
So the data's okay with you listening over a VLF?
Well, you're not listening, you're listening between those frequencies most of the time. If you're listening on the non-directional beacon frequencies, then you're looking for things like sudden ionospheric disturbances and you know, the fade outs that happen associated with solar flares, things like that. Okay, another good one is Radio Jove. This one is 20.5 megahertz, roughly. There's nothing really magical about that frequency. It just happens to be a fairly quiet area. So you're looking for frequencies where you're not totally overwhelmed by HF, international broadcasts. And so there's good frequency range right around 20.5, and I think another one at 22.2, right in there, where typically you could set up the receiver to listen and expect to get some signals without a lot of interference. Of course, they'll probably put a transmitter on that next week, but yeah, this has been going on for years. NASA originally started the Radio Jove project maybe 20 years ago. And the Society of Amateur Radio Astronomers then kind of supports it and has done a lot to keep it going. And some of the programs, like my lead-in slide, that first slide that had the pretty blue picture of the galaxy, that was done by him out in Hawaii, KH6SKY, Jim Sky. And so he writes programs that actually record the Jupiter and solar type things from receivers. But basically anybody with an HF dipole at that frequency can hear something. But it's easier if you have a way of tilting the angle up so that you're not hearing so much thermal background from the Earth. Question in back?
Would you listen to AM mode and what bandwidth would you listen to and all that?
There's a couple of key things here. Anytime you're listening to noise in radio astronomy, you got to be able to turn the AGC off. It's usually AM and as wide a bandwidth as you can get. So more signal is more bandwidth when you're listening to noise. Okay. All right, let me move along here. Okay. These are some pictures of solar flares. Okay, here's an audio of a solar flare. Basically that elusive. It sounds just like somebody turning up the noise and then turning it back down. So yeah, you could fake it. You could make that happen. But these characteristic traces are really what you see when you look at a solar flare. They typically have a real fast rise time and then a slow fall off. And so once you see those in the graph, it's easy to pick out that versus interference. Okay. This is a typical radio Jove dipole array. Got two dipoles here with a cable TV two-way power divider as a summer, and it sums the two together with a particular length coax, so that it actually focuses up and moves the beam up onto the sky more. So you're trying to point at Jupiter, or where Jupiter is going to go through in the sky. And let's see, you get two characteristic signals, L burst, which sound a lot like ocean waves, and then S burst that sound a lot like popcorn or ignition noise. That's another one to remember. Turn off the noise blanker because it's liable to take some of this stuff out. So no AGC, got to have a real stable receiver, quiet area, and then just you're just taking the audio into a sound card and recording it into one of these graphic programs. Okay, let's listen to the L burst. And that's the one that sounds like ocean waves. You probably realize you've heard this before if you've been on that frequency on HF. Yeah, this one's a little lower. You might have to turn it up more. Okay, let's switch to the S burst now. radiation noise, only a little different. Or a lawnmower, yeah. Okay. All right. Let's move on from that one. What we were doing was using that receiver kit that was in the picture to show students how to do soldering, and then they were actually building the antennas and using that to pick up solar flares when this was done. This was at the observatory there in North Carolina when I was working there. This is the culprit that creates these noises. L burst and S burst are caused by the magnetic field around Jupiter interacting with the moon Io. Io apparently has a lot of sulfur, and it's close enough that it gets kneaded by the gravity that's going through until it's got sulfur volcanoes happening and throwing a lot of sulfur, ionized sulfur, out into that orbit. And so there's something going on there that causes it to be like a giant generator. The magnetic field and that moving moon going through it. So you can predict when these Jupiter storms will happen based on position of Io, which direction it's actually beaming the signal. Okay, and that's just the dual dipole details. Some different kinds of Jupiter signals. All right, and I went over this. Quiet radio location is the hardest one to get for everybody in this group, probably. You got too many close neighbors and too many computers today, so you'll be really lucky if you have, you know, a really quiet location, but you can work at it, usually get it. Okay, let's see, most, yeah, computers. Software-defined radios, big in radio astronomy. FunCube dongles. These are about what you'd expect. You can receive with them. You might do radio astronomy, but you get what you pay for. It's like a $20 HF receiver or a $20 VHF, UHF receiver. Everything's going to overload it. So I don't recommend these, but they might work. Okay, that's a typical signal that you might see sweeping across the galactic plane. A lot of the dish type stuff, especially 1420 megahertz, we just point the dish at a particular spot and then let the sky move in front of it. So it's a very slow measurement. So 2 hours to do this this graph here.
But you have to be in a quiet space.
Okay. All right, let's move along. Meteors, meteor scatter. I don't know if anybody's done meteor scatter, but you're basically just listening for signals. And let's play. This is what it sounds like you're listening to a reflection. Yeah, play that one again. So you're hearing the reflection off of a meteor streak, and you're hearing the frequency change as the speed of the meteor slows down. So on 2 meters, that might make a 15-second signal that you get a couple of those, you'd make a QSO. Okay, I think we're coming up to the end here. And so all the links and stuff will be on the presentation on the website. And any other questions? Okay.